All right, the last module here, section 4, is subnetting. I couldn't decide if I wanted to put this into the course or not, but I decided eventually to put it in. I hope that this is going to be taught in a way where you can really understand subnetting and it's more easy to digest, and hopefully I'm able to teach it to you in a way that you can start doing it in your head, or at least have a basic step to write it out where it's extremely clear. So before we get into how to subnet, we have to cover key terminology. So we have CIDR notation and subnet masks. CIDR notation stands for classless interdomain routing. It's a notation that we write in the form of slashes. So we're going to see this, but CIDR notation, it's also called a hack. So if you said, we have a hack 8 network, it's a slash. It's a CIDR notation. It's a way of representing IP addresses and network prefixes in a more flexible way than traditional class-based addressing. The IP address is going to be followed by the slash and a number to represent how many bits are allocated for the network. In doing so, it also tells you how many bits are allocated for the hosts, which we'll get into. The other thing to be aware of is subnet masks. The subnet mask is going to be a 32-bit number used to divide an IP address into network and host portions. Everything is going to be broken out into either the network side for allocation or the host side for allocation. The mask is going to be represented for something like this in a decimal format, and it's going to use 4 8-bit notations for each octet represented by the dots separating the octet. So in IPs, we have 4 octets separated by the period. So this is octet 1, octet 2, 3, and 4. The subnet mask is applied to the IP address using a bitwise AND operation to determine the network portion of the IP address. In doing so, we also get the host side to it. This is going to make sense in the coming slides. So let's cover some mask examples and our hacks/CIDR notation. So if we remember way back in Module 1, we drew out this diagram of 128, 64, 32, 16, 8, 4, 2, 1 to learn how to convert decimal to binary, binary to hex, etc. You should be very familiar with this, and if we break it out and apply it to IP addresses, the concept is still the same. So we're going to take the same nomenclature that we've had here for our 8 bits broken out, and we're going to give them to each octet. So if we just draw some lines here, this is octet 1. Probably should have started with the fact that we're using this sample IP address of 72.118.1.1 with a subnet mask of 255.255.255.0, and we're going to get to this answer of what the hack would be. Just bear with me. This is the IP address 72.118.1.1. IP addresses are broken up into 4 octets, so we are just drawing the lines here for each octet, 1, 2, 3, and 4. Now, we start with identifying what the hack is, the CIDR notation. This is how you figure out the CIDR notation. Now, if we remember, we'll pick a different color here. Converting this number, 72, to binary, we would ask ourselves, does 128 go into 72? No, it does not. Does 64 go into 72? Yes, it does. So we would allocate this bit as on, and we would subtract 64 from it. Then we would have 8 left over. So 32 does not go into 8, nor does 16. 8 does, and we would have 0 left over. So 72 converted from decimal to a binary would give us 0100100. If we did the same for 118, 128 does not go into it, so this would be 0. Then we would have 118 minus 64. We have 54 left over. 54 minus 32. We would allocate that. We have 22 left over. 22 minus 16 gives us 6. 8 does not go into 6. 4 does. We'd have 2 left over and then none remaining. So 118 would convert from decimal to binary in this, And then 0 is very easy to calculate. And we would have this be repeated here. So this is 72.118.1.1 converted from a decimal IP to a binary IP. So we've reviewed that. We know how to do that. That was way back in Module 1. Now, what we're going to build on top of that is our hacks. So we just covered subnet masks, and we explained that they're a representation of what's allocated for the network piece and what's allocated for the host piece of the address. So let's get into that. Our hacks are defined by following the same nomenclature we have above. So starting with the first bit over here, we will give that the value of hack 1. This would be hack 2. This would be hack 3, 4, 5, 6, 7, 8. We're still working with the same 8 bits. We're now just giving them a CIDR notation of our hack. They continue to escalate and just increment by 1 as we go across, and you can have a range from hack 1 all the way to hack 32, which should make sense because 8, 16, 24, 32. So if we wanted to calculate out all of our hacks for all of the bits that are available to be assigned in an IP address, we map them out accordingly. So this is hack 1, 2, 3, 4, 5, 6, 7, 8. This 128 would be hack 9, hack 10, hack 11, 12, 13, 14, 15, hack 16. This one would be hack 24, and then all the way to this one, which would be hack 32. Hopefully that makes sense, as the hacks are not going to change. You're always going to have the same range of 1. This bit is always going to be allocated for hack 1. This bit is always going to be allocated for hack 32. These do not move around or change. Whatever bit they are assigned to, that is what it is. So if we had this example of 72.118.1.1 hack 24, our hack 24 is allocated right here. So that means that all of the bits prior are turned on. And if we remember, if we allocate as true or turned on for all of the bits, the highest value, if you add all of these up, would be 255. So since we're working with a hack 24, we allocate the bits and we turn them all on for every single bit allocated for the CIDR that is being allocated. So all of these turned on give us 255, 255, 255. We're not working with hack 25, so this remains 0. So that means the network mask, the subnet mask of a 72.118.1.1 hack 24 will have the network mask of 255, 255, 255.0. This indicates that the first 24 bits, so 8, 16, 24, represent the network allocation. That means that these first 3 octets here, since all of the bits are turned on, these do not change. This will be very apparent when we get into our examples. The only octet that can change is the one that isn't being worked in. So we're working in the first 3 here. All of these bits are allocated to the network side. The only ones that we can, play with or assign to hosts are the ones from hack 25 all the way to hack 32. So we can have a combination of an IP address of .1 to .255 be represented in this last octet. So this octet, pick a different color, is assigned for our host allocation, whereas the pink is assigned for the network allocation defined by our CIDR notation. So first 24 bits, aka the first 3 octets, is the network side, as defined by the hack 24. And the last 8 bits over here, the 4th octet of the IP address, are allocated for host allocation, for what we can give our host for IPs. Now that I've thoroughly confused you for just going over subnet masks and hacks, let's get into the examples, and it should become a lot clearer as we work through them. Okay, starting with examples. This is a chart here for subnet masks based on CIDR or hack notation, and it's giving you the value for the subnet mask for how we would denote it. Let's work through some of the examples here. We have 192.168.0.0 hack 16. So if you remember, this is hack 1, hack 2, 3, 4, 5, 6, 7. This is hack 8, or 1. We would have hack 9, hack 10, hack 11, 12, 13, 14, 15, hack 16. So that's where we're going to, hack 16. So that means we were working in our first two octets. So all of these bits and all these bits are allocated. That means that this is 255 because we add all these up. This one is also 255. And we're stopping at hack 16 because that's what the first example is for. And this side, octet 3 and 4, are allocated for the host side. This is our network side. So the subnet mask for this IP address would be 255.255.0.0. Oh, sorry, that's no dot there. But as you can see, if we go down to hack 16, we get exactly that, 255.255.0.0. Let's do another example. We have hack 24. It gets easier to do this if you just remember that this is hack 8, this is hack 16, this is hack 24, and this one is hack 32. Just so you don't have to count out individually and kind of jump ahead. So 8, 16, we're working with hack 24. That means that this one is allocated and all of the others are also allocated for all ones. So this means this is 255.255.255. That's reserved for our network side. And then our host allocation gets a 0. And again, we have IP address of .1 to .255 to give to our hosts. If we check our math for hack 24, we go over here, 255.255.255.0. Perfect. Keep working through these. Let's do one that doesn't end in a nice octet. So we have a hack 9. If we remember, this is hack 8. That means 128 is our hack 9. So what do we do with this? The same principles apply. All of these bits, 8 bits, are allocated, so that gives us our 255 dot. We only add up whatever bit is allocated. So we're working with hack 9. This would be hack 10, 11, 12, 13, 14, 15, and 16. None of these hacks are allocated, so they're all zeros. The only one that is allocated for the network side is hack 9, so this 128 would be allocated, and if we add all of the bits up, that gives us 128. None of these are allocated, so that gives us .0. None of these are allocated, it gives us .0. We're working with hack 9. If we go to our chart, our hack 9 gives us 255.128.0.0, and that is how we arrived at that subnet mask with math for, again, converting decimal to binary. Moving forward with hack 10, pick another color here. If this is hack 9, that means the 64 here is hack 10. So now we're working with also allocating this bit and this bit. None of these bits are allocated. So this one remains the same at 255.128 plus 64. That gives us 192. So this is .192.0.0. If we go to our chart, hack 10, 255.192.0.0. Do one more example here of hack 32. I'm calling out the hack 32 example here because I want you to grasp something important. As you know from the chart, you can have a range of hack 1, all the way to hack 32. But if you have a hack 32, that means that all of your bits are allocated. So your mask would be 255.255.255.255. That means all of the bits are allocated for the network and you have no bits for the host side allocation. Your only host IP that you're able to work with is whichever one is written out in the IP notation. So this hack 32 is significant because I want you to realize when you're reading the IP address, there are no subnets you can make from a hack 32. The only IP address available is 14.15.16.17. You can't make any more host IPs available to it because all of the bits have been allocated for the network, so that is what you get. That's the one IP. Hopefully that makes sense. If you ever wanted to give someone your IP, let's say mine was 17.28.52.11, it's the same as telling them my IP is 17.28.52.11 hack 32 because it's not used as a subnet. It's fully allocated. All of my bits will never change. It's fully allocated. All of the bits have been given out to it as denoted by the hack 32. Stick with me. We're gonna keep pressing here. You might have to watch this 1 or 2 times, but I have faith that you're gonna be able to pick it up. Anyone remember our private IP class ranges? This should make a lot more sense now because when you see this denotion here of the CIDR or the hack, it makes more sense now as to why Class A is such a larger network than a Class C network. These range from largest to smallest. And let's see why that is based on what we just learned. So hack 8 is allocated for our Class A. That means we're working with right here. So this is allocated to the network, whereas all of these bits, .0, .0, .0, are allocated for hosts. If we keep working down the progression here, Class B is a hack 12. So this is hack 8, 9, 10, 11, 12. That means all of these bits are allocated for the network, and all of these bits are allocated for the host. As you can see, there are less bits in the Class B address range to work with to give to your hosts, so it is a smaller network as there are just less number of hosts that can be allocated for the IP addresses. If we take a look at Class C, it is a hack 16. So this is our hack 16 value here. That means all of these bits are allocated for networking, and we have even less host bits. We only have 2 octets worth of host bits to work with to assign out to our devices on our network. So this is the smallest class range we can have because more bits are allocated to the network, whereas in hack 8 for Class A, we're only taking up our first octet for the network, whereas in Class C, we're taking up the first 2 octets to designate towards the network. So here we have 3 octets to work with for host allocation, any combination of 1 to 255 for 3 octets, and here we're losing an entire octet. We only have that number of combinations to work with, which is a significantly smaller number. So it should make sense now to not have to memorize whether it's hack 8 or not, because as we mentioned, whatever octet we're working with, so if this is our hack 8, the number in the IP address for that octet denoted by the CIDR does not change. Every single IP address in a Class A network is going to start with 10 dot. Same for a hack 16. Every number in a Class C IP range is going to start with 192.168 because these bits have been allocated to not change for the network range. The only octets that are going to change are the ones allocated for your host bits on the network. Same with hack 12. But instead of it ending on a nice even octet of 8, 16, 24, or 32, it lands on a hack 12, so 9, 10, 11, 12. So that's why it's 172.16 to 172.31, because when you break that out, you're allocating this much for the network and this much for the hosts. Okay, let's get right into it. Let's do the examples here. We have enough knowledge where we can now learn subnetting. The first thing that we do is always write out our 128 to 1 allocation for our 4 octets. So these are our 4 octets. I left these numbers in here. I really couldn't decide to leave them in or out. I don't want to confuse you too much, but this is basically just adding together your subnet mask. If you also wanted to calculate back the subnet mask for the range for each of the NFLBs that we're going to come up with, 128 and 64 gives you 192. Plus 32 gives you 224, all the way up to the full allocation of 255. If you don't want to look at this right now, that's fine with me. If you do want to look at it, I included it, and you'll see it'll move around based on what octet we're working with. But anyways, back to our example, 192.168.10.70, hack 28. We've drawn out our 4 octets for all of our bits that we have available. The next thing we do is find out where hack 28 lands. So 1, 2, 3, 4, 5, 6, 7, hack 8, hack 16, hack 24, 25, 26, 27, 28. So we are working with our group assignment, probably just call that out, group, allocation of 16. This is going to be key in figuring out what our network address is going to be, and we need to identify this first. So we took our hack 28 and we mapped it to this bit in the last octet for the value of 16. The next thing that we want to do is calculate out where we're working with in our octets. So since all of these bits are allocated, since we're working with hack 28, we know that 192 is not going to change. We know that 168 is not going to change. And our third octet, the .10, is not going to change. Since we're working with hack 28, we're falling within our 4th octet. So the only number that is going to change when we get our answer is the value within the octet where the CIDR lands, and that's going to be our .70. So if we take all of that in mind, remember we were at 16 for hack 28. We are now determining that we're working in the 4th octet. We need to start counting from 0 to 16 until we figure out where 70 falls between. So we have 192.168.10.0. These octets are not changing. We're only working in the last octet, and we're starting with 0. We always start with 0. The next highest range we can have is 192.168.10.16. Each time we're going to add 16. 192.168.10. 16 and 16 gives us 32. We're trying to get to 70. 192.168.10.32 plus 16 gives us 48. 192.168.10.48 plus 16 gives us 64. Dang, we're still not there. This is a terrible example. 192.168.10. 64 plus 16 gives us 80. Okay, so 70 falls between 64 and 80. So we know we have found where we need to be working in. These are all the available networks that you can have based off of a hack 28. But since we're working with a .70, we needed to increase our networks by 16, since that's what's the group allocation defined by a hack 28, until we found where 70 would fall between. Now that we have found that, this means the lower number, 64, that is our network-based IP address. So when we do subnetting, I go the route of NFLB, big football fan, go Eagles. We have the network IP, the first IP that you can allocate, the last IP that you can allocate within that network, and your broadcast IP. And usually we draw a little line at the bottom. So now that we've identified our network IP, this is going to be 192.168.10.0. 10.10.64. Getting the first IP is very easy. All we do is add 1. So 192.168.10.65 is our first IP that we can have. Since this bit is reserved for our network IP, we need to add 1 to get our first IP that we can use to assign to our hosts. The next thing we calculate is the broadcast IP. We get the broadcast IP from the higher range of what the next available network would be and subtracting 1 bit. So if I wanted to get the broadcast address for the last available bit before I got to 192.168.10.80, I need to subtract 1 bit. What that's going to look like is it's going to be 192.168.10.79. 79 is 1 less than 80. And to get the last bit available, we always reserve 1 bit for the broadcast and 1 bit for our network allocation. We just subtract 1. So the last IP that I can have assigned in the range is going to be 78, and we're not working in these octets, so 192.168.10 will remain. The .64 is our network IP allocated. The first bit that we can assign out to host is the .65. The last bit that we have available to assign out to host is the .78, and our .79 is our broadcast IP. Let's do some more examples, and hopefully it gets clearer as we go along. Okay, 10, 20, 30, 150, hack 18. First thing we do, where does hack 18 lie? So this is hack 8, this is hack 16, 17, 18. We're working with this 64 right here. We've identified that we're working in the third octet, so we know that 10 is not going to change and 20 is not going to change because these bits are fully allocated. We're working with 30. So now we're trying to get to 30. So let's write out our combinations here. We can start with 10.20. We always start at 0, so we're doing 0.0. The 150 changes to a 0 because these are all allocated to hosts, and we always start at 0 when we're trying to figure out where the first network IP is allocated to. These two do not change because they're reserved for the network bits. So then we have 10.20.64.0 because we're incrementing by our group allocation value of 64 as denoted by hack 18. We're looking for the range in which 30 falls in, so we've already found it. It's between 0 and 64. If we were to continue, it would be 10, 20, 64 plus 64 is 128.0, and then if we went one more to find the last available range, 128 plus 64 is 192, that would be .0. We've identified that 30 falls between 0 and 64, so that means our network-based value is 10.20.0.0. The first bit, we just add 1, so 10.20.0.1. The next thing we do is calculate the broadcast address. We take the next available network that we would have had and subtract 1. So this is going to be 10.20.63.255. Going to pause here because it's different than the first one, which was a bit easier. If you have 64 and you're subtracting 1, you're actually borrowing from the last octet. So you need to keep in mind it's going to be 63.255 for our broadcast allocation because that is 10.20.64.0 minus 1. And then our last IP that we give it, it's 255 minus 1. So it will be 10.20.63.254. Hack 18 subnetted. Am I losing you? I can't tell. We're gonna keep going. Next example, 172.16.18.50, hack 22. First things first, figure out where hack 22 lies. Hack 8, hack 16, 17, 18, 19, 20, 21, 22. So we're working with our 4 group allocation for hack 22. The next thing we do, write out our groups of available networks starting with 0. We know that we're working in the third octet, so the first 2 numbers are not going to change because they're allocated for the network. 172.16, start at 0.0.0. 172.16, since we're working with 4 as our allocation, we increment by 4. So we have 4.0. We're looking for where 18 is falling within. So 172.16, 8.0, 172.16, 12.0, 172.16, 16.0, 172.16, 20.0. 18 falls between 16 and 20. That means this is the network IP that we're working with. So 172.16.16.0. The next thing is finding the first IP we can allocate, so we just add 1. 172.16.16.1. We find the broadcast address next. We subtract 1 from 172.16.20.0. That's going to give us 172.16.19.255. To get our last bit, we subtract 1 from the broadcast. 172.16.19.254. Are we making sense yet? We got one more. Maybe you need to watch this a couple times. Hopefully this is a way that's teaching it to be somewhat digestible and you can create your own random IP addresses with random hack notation to figure out if you get the correct answer or not by asking Google. Because at the end of the day, we have calculators for this, and if someone asks you how to subnet on an interview question, I wouldn't want to work for them anyways. I'm just joking, but I do think that's a ridiculous question to ask, especially when we have Google. But it is important to understand how to do it and where it comes from, so general knowledge, I'm all for. Last example, 10, 155, 55, 128, hack 9. Where does hack 9 fall? This is hack 8, so hack 9, we're working with 128 as our group allocation number to increment by. We're working in the second octet, so I know that the 10 is not going to change as that's allocated for the network, and I'm looking for 155. So we start 10.0.0.0, increment by 128, 10.128.0.0. We're looking for that 155, so we have to go to another one. 10.128 plus 128 is going to give us 256.0.0. But wait a minute. 256, that is outside the max range of 255 if all 8 of our bits are allocated. Extra points for you if you noticed that. If you just said 256 and didn't think anything of it, well, it's fine, but it should have looked odd to you. So keep that in mind. We've now found where 155 falls between. It's between the values of 128 and 256. So our standard operation is still in place. This means this one is our network IP, so 10.128.0.0. The first IP that we can allocate, we just add 1, 10.128.0.1. The next thing we do is find the broadcast. So this is where it gets interesting for this example, and it's why I included it. 10.256.0.0 minus 1 is going to give you 10.255.255.255, because you're borrowing from the second octet you're actually borrowing from the 4th octet, which affects the 3rd octet, because you're minusing 1 bit from everything that's allocated. And this should look familiar because our broadcast IP has always been 255, 255, 255, 255. So all of our broadcast IPs, I just thought this was a good example to put in here. And then our last IP that we can allocate is going to be this, the broadcast, -1. So it's going to be 10.255.255.254. And there you have it. Hack 9. Hopefully this module has introduced subnetting into a way that you're able to manage it, you're able to understand subnet masks, you're able to NFLB out your example, work through it, draw out where all of your bits are allocated, where all of your CIDRs fall, follow the same methodology, start at 0, increment by your group allocation number, define by your CIDR, and then get your network address first, add 1 to get your first IP, calculate your broadcast next, and then it's -1 for your broadcast. So hopefully this was digestible. Thank you so much. If you made it through the networking mod, congratulations. You really, you deserve it. Congrats.